Afternoon. Welcome to the May Children's and Women's Lunch and Learn session hosted by the BC Children's Hospital Research Institute and the Women's Health Research Institute. Before I go ahead and introduce Dr. Bone, I just wanted to take a moment to acknowledge the traditional lands with which we're coming from today, located on the ancestral and traditional territories of the Coast Salish people, specifically the Musqueam, Squamish, and Tsleil-Waututh Nations. And we're very grateful for the opportunity to live, work, and learn on these sacred lands. This afternoon, we have Dr. Jeff Bone presenting. Dr. Bone is an investigator at BC Children's Hospital Research Institute and the biostatistical lead at the Research Institute. His research focuses on the intersection between modern statistical methods and applications in clinical and epidemiological research, aiming to generate robust evidence for improved decision-making. His research activity is split between exploration and dissemination of statistical methods and collaborative research with clinical and public health colleagues. In the latter, Jeff works particularly in areas using administrative data sources and on the design and analysis of randomized control trials. So without further ado, we'll turn it over to you, Jeff.
Thanks, Shanley, for the intro, and thanks for inviting me to give this talk. I'm going to talk about almost none of those things that you mentioned in my bio. This talk is called Musings on Statistics and Clinical Research, and it's because that's mostly what it is. I'm just going to talk about some things, some related, some unrelated, that I see often in medical research that I have some opinions on. So you're subjected to 45 minutes of my opinion. So I'll start with a disclosure that of just that. This talk is based entirely on my own views and does not reflect the broader biostats community. So maybe some other statisticians will agree or disagree with some of these thoughts, but you're stuck with me for today. So to give you a little overview, I'm not going to try to put an intro to biostats into 45 minutes. I'm going to assume that everybody's sort of seen some of those things in the past. Instead, I'm going to discuss some common misconceptions and statistical principles that I think are important, or that I see across the number of projects I've worked on over the last few years. And there are many options that I can talk about, but for today I've chosen 10 to go through. And as I said, these 10 are a little bit disjoint, but some of them have a bit of a common theme to them. And my plan is to just go through each and talk a little bit about what I would consider best practice or good things to think about when you're designing and analyzing studies. So number one, I'll start with something simple that I think most would agree on. And that is that whenever we have a data set, whenever we get a new data set, or we're working on examining some data, it's important to never skip data visualization. I could go on and on about good practice for data visualization, but I'll show a couple of examples of why this is important. So let's imagine we have two data sets of people's ages. So we just collect a whole bunch of people's ages, and we're told the following summary. You can see data set A and B is each row in the table. You can see the minimum values are quite similar. They're around 17, 18. The interquartile range, the first and third quartiles are similar to within a couple of years. The median, maximum, and average or mean ages are all the same. So based on this table, you likely conclude that you have two very similar cohorts of people, at least in terms of their ages. But if I make a graph of these two data sets, which you see on the right, I have data set A and data set B, it becomes immediately obvious that these are two very different distributions. First one, group A, is sort of this bell-shaped or normal distribution that centers around the average age of 50. And the second data set is actually sort of two distinct buckets. People sort of in there, mostly 25 to 35 and mostly 65 to 75, with some little tails at the end, and almost no one or no one in the middle. And so right away, if we had just had the previous table, or if just a previous table was reported in a publication, we'd be tempted to conclude these two groups were the same when in fact they look quite different. This is a little bit of a contrived example, but shows you how two different distributions can give rise to the same sort of summary statistics, which is usually one of the very first steps in any analysis, is sort of creating those summary stats. The other thing that these visuals can be useful for is detecting outliers, implausible values, or errors. So for example, if we saw someone in this data set with a negative age, we would know that's an error. We know that age starts at 0. Similarly, if we saw someone who was 200 years old, we'd be inclined to investigate that data point, as that's sort of an implausibly large value. Those are not always things that you see when you just make summaries of the data. Often it's something that only comes out when we make a lot of graphs. The other thing that I'll talk a little bit less about today, but just to point out, is that actually sometimes when we fit quite complicated statistical models, we can graph the results of those models in a way that is more clear than a table full of numbers. So not only is this useful at sort of the exploratory data analysis stage when we're just trying to understand the patterns in our data, but it can also be used to translate complicated results into nice images. Another little example of this is this famous quartet of data sets called Anscombe's quartet. So you can see that we have 4 different graphs, each with the same X and Y axes. Each of these orange lines has exactly the same slope, exactly the same intercept, and the correlation between X and Y is 0.82. It's exactly the same in each of these 4 data sets. So here we have the exact same statistical model. If we were to fit a line to each of these 4 data sets, we would have the exact same model. But as you can see, the patterns in the data are actually quite different. In the first group, we have sort of a random scattering around the orange line. In the second group, we have a bit more of a parabolic shape. The third group is almost a perfect line with the exception of this one outlier point at the top. And the fourth group is a clustering of points all at one x-axis value with a single point out here. So here's an example where the same 4 data sets give rise to the exact same fitted line or the exact same statistical model, but actually have quite different patterns. And how you would interpret the results of this model would be quite different depending on which of these 4 data points. So it's useful at both the exploratory stage and also, drawing, in this case, model fits to the raw data. So number 1 is not to skip data visualization. In most projects I work on, I make, 10, 20, 25 graphs of various things just to have a look at the data to understand it before I move forward with any sort of analyses or before I present results to collaborators. I may not share all those graphs, but at least internally, they're quite useful to me to understand the patterns. So it's always worth spending a little more time up front and given a project on this kind of work. So that's number 1. Never skip your data visualization if you're ever working with a new data set. Number 2, and this is one that I often sort of hammer people on when I'm learning about a new project, is to ask well-defined questions. The same data set can often be used to answer different types of questions, and it's important to be fairly clear before you start any analyses which sort of bucket of questions you're falling within. And I like to think about clinical questions falling into one of three different categories. The first is descriptive. And this honestly covers the majority of projects or questions that you see or papers that you might read. And these are sort of questions like, what is happening in a population? So for example, how many kids in BC have type 1 diabetes? Or how many kids in BC were admitted to the hospital last year? How many, pregnant women delivered at home last year versus in a hospital? These are descriptive epidemiological quantities that can be quite useful for surveillance or understanding sort of the scope of various problems. The other type of descriptive question is often around who developed worse outcomes. So trying to indicate within a population which groups are doing better or worse. So for example, are people with certain factors having better or worse outcomes? These are not making predictions. These are not making causal statements. They're just describing what's happening in a given population. The second type of question we can ask is what I would call predictive. So this is about what will happen in the future. So which patients will develop worse outcomes in the future? And these questions can be sort of in two different buckets. One is looking at, say, individual risk factors. So do older patients do worse? Do patients with high blood pressure have higher rates of, say, cardiovascular outcomes? So that's a lot of like, sort of clinical history or looking at very individualized risk factors. The other type of predictive question we can ask is, can we build a statistical model that incorporates multiple factors and multiple sources of information to make some risk stratification in the future? So given a whole bunch of patient factors, can I put them through some sort of statistical or machine learning tool and get a prediction about what's going to happen in the future? And so this moves from the descriptive, what happened in the past, what does the population look like, to can we make guesses about what's going to happen in the future based on patient factors. The third type of question is causal. And this is sort of, as the name implies, about causal effects. So does treatment X or decision X or a certain exposure alter some outcome? So for example, if you smoke cigarettes, does it cause lung cancer? We've established, through many studies that is a causal relationship. This is usually the hardest type of question to answer for numerous reasons, which I'll touch on later. But a lot of confusion in clinical research comes from the wrong framing or the wrong interpretation. And in particular, you'll see many papers that answer a descriptive question, but subsequently write the discussion or summarize the results in a way that applies causal reasoning. And you see this in a number of different areas. So it's really important when you're starting a project, and especially for me as a statistician, when I'm talking to someone who's starting a project, I'm trying to sort of triage where their question lies and how well that question is aligned with the data that they have or plan to collect. So I think it's always useful to take that extra moment at the beginning of a study to make sure that you're asking a well-defined question and you have a clear sense of how you plan to use those results, rather than sort of approaching things in a bit of a more casual way, and then say, for example, writing and using causal language. So it's important to be cautious and careful about how we frame questions and how well they're aligned with our data. Sort of related to that is number 3, which is that bigger is not necessarily better when it comes to statistical models. You'll see in many applications, people throw a whole bunch of variables into a statistical model, usually a regression model, and then sort of interpret everything in that model as having some sort of relationship with the outcome simultaneously. This meme on the right sort of describes that approach to model building. This scientist here has a whole bunch of risk factors and is just sort of tossing them together in this bowl, which represents a statistical model, and ending up with a sort of causal salad. And the problem with this is almost nothing in that model is going to be directly interpretable unless it's well thought out and reasoned based on prior understanding, prior data, thoughtful consideration for how these different risk factors go together or don't. Generally speaking, for descriptive questions, which cover the majority of studies that I see, simple, well-specified models usually give you more detailed information or more interpretable information. So sometimes less is more when it comes to building statistical models, and it's not always the case that, say, putting everything you're interested in into one model is the best way to answer a question. The fourth thing I'll talk about that sort of builds on this idea about how to build models is that it's not all about p-values. So as you can see, there's a little cartoon here. I imagine everyone in this room has seen a p-value or written a paper or been involved in papers that use p-values. My guess is that probably less of you would feel comfortable explaining statistically what a p-value means. Nonetheless, these are probably the most pervasive statistics that you'll see across the biomedical literature. So formally, a p-value is the probability of an observed or more extreme result, assuming the null hypothesis is true. To say it in a different way, assuming that there's no effect or no relationship in your data, what's the likelihood that you would observe a data point that you see in your current data set? So the further away from no effect your data point is, the less likely it is if you're assuming that there's truly no effect. Graphically, what you see here is that the most likely observation is the null, the sort of middle of this curve. We observe a point over here, and the p-value is this green shaded region. In general, these are hard to explain, and if you didn't fully follow that, I don't blame you. Even for statisticians, this concept is one that we have to read again and again. But nonetheless, this statistic still finds its way into almost every paper that you'll see. On the face of it, that's already a problem to me. I prefer things that are easy to explain. But we'll see that through some examples, there are other ways that p-values can be a little bit misleading.
Jeff, I'm just going to interrupt you for a second. Your floating head is blocking the slides. Is there any way for us to switch that on our individual computers? I don't think so, at least not on mine.
I don't know. Maybe I'll stop sharing for a second, remove my floating head.
It's a beautiful floating head, though.
Is it better now if I've tried to move something? Is that any better?
No, you're still right in front of the, what's on the slide.
Thank you for telling me that. Do you need my floating head? Or can maybe I'll just be a voice.
That'll work too. Okay, that's perfect. Okay. You're good now.
Okay, I'll bring my head back at the end, but for now, I'll just be a voice. So to say, the first piece I'd like to say about this is that statistical significance, while often emphasized, is not the same as clinical relevance. So specifically, what you'll often see in papers is that a p-value less than a certain value, often 5% or 0.05, is taken as some sort of meaningful finding. But this does not actually tell you anything about the size of an effect, whether that effect is real, whether it's important in the application we're looking at, or whether it's something that's likely to be replicated. All of those things actually need context, nuance, and typically a more fulsome assessment of the data at hand. So just running some statistical tests or models, summarizing the p-values and then interpreting the result as important or not based on those can often obscure rather important findings or overemphasize findings that actually don't have much relevance. And we can see that in this little example I have here. So here's a graph that summarizes two studies. The first one in blue has a p-value greater than 0.05. It has a relatively small sample size. The observed effect is quite large. And you can see here this blue bar, this is the confidence interval is relatively wide and crosses the null. So here's a study with a large effect, but it's relatively small. It's not a significant p-value, but certainly the effect is clinically important. The second example is a tiny effect. So you can see basically the effect is right near 0, but it has quite a small p-value, largely due to the very big sample size of this study. So the second study is statistically significant, but the effect is clinically unimportant. And this is because p-values change quite dramatically with the sample size. So the bigger a study you have, the smaller all comparisons p-values are generally going to be. While the smaller the study you have, the bigger the p-values are going to be, sort of regardless of the size of the effect. Personally, in this example, I'd be more interested in the finding from study A with the small sample size and large effect than I would be from study B with the very small effect that has quite a small p-value. So it's important to not just differentiate. If we dichotomize these two results and said the first one is not important because the p-value is large, the second one is important because the p-value is small, we'd actually be missing some fairly important differences and nuance between them. So in general, we want to be cautious about over-interpreting sort of dichotomized significance testing. And so what can we do instead? What we'd like to do instead is report the details. And that's the fifth thing I want to talk about. So what some papers report is risk was higher in group A, say, compared to group B with p less than 0.05. So this would be a sentence you'd see in some results sections of clinical papers. This sentence doesn't tell us anything about whether the effect is relevant, as we saw in the last graph. It doesn't tell us if it's a big effect or a small effect. And it doesn't mention how precise the study is. So how in this case, narrow the confidence interval would be. So this is one way that you might see results presented in an abstract or results section. But what actually would be more informative is some detail on these things. So for example, risk was 80% higher in group A compared to group B. So this translates to a risk ratio of 1.8. We provide a 95% confidence interval. This speaks to the precision of the study. The more narrow the confidence interval, the higher the precision. The wider the confidence interval, the lower the precision, which is determined largely by the sample size, and the exact p-value rather than a dichotomized version. And how I would summarize this is that the study data were most consistent with an 80% increase in group A, with data compatible with between 40 and 120% increase. Those are the two bounds of the confidence interval. There's no mention here of statistical significance versus not. It's just saying, here's how much higher the risk was. Here's the range of values the data were compatible with. And the sentence describes those things completely. So when you're reporting, it's always preferable to give an effect estimate, like a risk ratio, odds ratio, mean difference, a confidence interval, and a p-value, as opposed to just some sort of specification of a significance test. This way, the reader can see actually how large the effects were and not focus on simply whether the p-value was small or not. So those last couple of slides are meant to illustrate when we're building models, we don't necessarily want these big giant models. Sometimes smaller is better. When we report those models, we want to report out detailed results about the study groups and not just dichotomized p-values. And that the p-values in general don't tell us anything about the size, direction, or precision of the effects in our study. So always better to provide greater detail and interpretation that focuses more on the data and less on an individual hypothesis. I continue to see many papers that report what we see on the left-hand side of this slide, despite, many statisticians encouraging more on the right. So when you're reviewing your own papers or papers you're working in, encourage the presentation of effect estimates and confidence intervals where you can. The next point or misconception that I'll touch on is about error. And this is that, largely speaking, random error is not usually our biggest worry in clinical or epidemiological research. So whenever we're conducting a study or collecting data, we can make two types of error. The first is measurement or random error, and the second is what's called biased or systematic error. Measurement error is basically we try to measure the same thing many times, or we collect some sample from a population, and there's some sort of randomness associated with that. So for example, if I weigh myself on a scale every single morning, there's going to be some natural fluctuation in the number of pounds or kilograms that I see on the scale. That would be random error. Some days I might weigh a pound more, some days I might weigh a pound less. There's no sort of clear pattern. A systematic error, on the other hand, is when we are consistently sort of missing the target in a specific way. So that would be, for example, if my scale was miscalibrated and every morning it told me I was 5 pounds heavier or 5 pounds lighter than I actually am. This would be a biased or systematic error. And the reason differentiating between these is important is because all statistical models, all statistical tests that we can run assume that the data you have are a random sample from the population of interest. Basically, it means that statistical models and tests can deal with measurement or random error. They deal with measurement or random error. They don't at all deal with systematic error. And unfortunately, in almost every study we conduct, we do not have a random sample from the population of interest. We have a sample that's available to us. So for example, if you're conducting a study at BC Children's and collecting data from charts, those are not a random sample of all kids with that disease or needing that surgery in the province. They're only those who had to come to BC Children's. So they might only live in Vancouver. They might have only been sick enough to come to a large hospital. Likewise, for deliveries at Women's Hospital, you might have some of the highest risk pregnancies referred to Women's Hospital. They're, again, not a random sample from, say, all deliveries in the province. So in almost every study I'm involved in, this is not true. Yet every statistical tool is designed to sort of deal only with random or measurement error. And the nice thing about random error compared to systematic error is by getting a bigger sample size, we can reduce that error. Unfortunately, this is not true for systematic error or bias. So again, we have statistical tools to deal with random error, and we can also reduce it by increasing our sample size. Those things are not true for bias. What you see on the right is sort of 4 different studies. The top right corner is the ideal case. This is high precision, low bias. So we have a big sample size and it's very accurate. The bottom right is low precision, low bias. We may have a small sample size, but it's an accurate sample. And the other 2 correspond to situations where we have high bias and high precision or low precision. And the important thing to note in the top left corner is that even when we have a very big sample or a very precise sample, if we have bias, we're still consistently missing that target. So getting more data doesn't help when you have a lot of bias. Getting more of the same data, I should say, doesn't help when you have a lot of bias. And so this is an area where, we sort of normally conduct all our analyses, assuming we're worried about minimizing random error. We conduct our studies to collect enough data to minimize random error. But actually, we should often be thinking more carefully about different types of bias. And the biggest culprits for the biases we should be worrying about are 3. The first is called selection bias. And this is who got into our study and why. So how did we end up with the participants that we have in our study? So for example, if I wanted to survey occupations in British Columbia, this Zoom room would have a severe selection bias because almost all of us work in healthcare. So we would say, if my goal was to summarize occupation types in British Columbia, I'd have severe selection bias here because really only one area of occupation is represented. The second type of error we worry about is confounding. And this is basically which factors differ between groups of interest. So if I wanted to compare one set of patients versus another, say one set of patients received a specific kind of treatment and the other patients didn't, it's likely that they're going to differ in important ways, those two groups. And those important ways need to be collected and handled in the data analysis. And the third type of systematic error that's important is measurement. And this is how accurately data are measured. So going back to my scale example, if I have a faulty scale, then I don't have an accurate measure of my weight. If I ask someone to self-report their number of alcoholic drinks per week, I'm relying on them giving me an accurate answer and not, say, over or underselling the true number. And importantly, none of these types of bias, as I mentioned, are fixed by statistical models or tests. So there's no regression model, there's no t-test that can deal with selection bias, confounding, or measurement. For selection, you have to collect the right patients. For confounding, you have to know which variables are important and measure them. And for measurement, you need to measure the data accurately. So these are only things that can be done at the study design phase and not at the data analysis phase. So it's important when we're planning studies, rather than only thinking about, say, how big of a sample size we need and trying to minimize random error, we focus on how we can minimize these other important sources of bias that can actually create much bigger problems than random error alone. So to give an example, let's say we wanted to do a chart review comparing all patients who were readmitted versus not readmitted after a hospital admission at BC Children's over the last 10 years. And this would be a big chart review. We'd have a very large sample, as there's many hospitalizations each year. So the random error is going to be very small. We're going to have quite a big sample, quite high precision, and low random error. But some things we'd have to think about is selection. This study would only include BC Children's patients, not those from other hospitals who say may be less sick. So if we were trying to study, the frequency of readmission, it might be higher at BC Children's because those are sicker patients. Confounding, if we're comparing those who are readmitted versus not readmitted, we'd need to understand what kind of conditions individuals were admitted with. So patients with more complex conditions would be more likely to be readmitted. So we'd want to understand those characteristics and see if we could capture them. And measurement, not all information is going to be in the chart, or it may be inaccurately captured. So if we're reviewing patient charts to try to capture detailed data, it might not always be there, or if it is there, it might not be as accurate as we'd like. So we'd have a really big sample for this study. We'd have a small random error, but we'd have some concern about selection, confounding, and measurement. And so when you interpret the results, you have to interpret them with these sort of issues in mind. One way to help with at least one of those issues, specifically confounding, is to randomize whenever you can. So this is point number 7 on things that I think are important, is whenever we can run a study, or whenever we're in a study situation where we're trying to compare two or more groups, whenever we can randomize people to those two groups, that is a huge strength. And it's a huge strength because it ensures that the groups are comparable. It ensures that they're included in the study in the same way. It ensures that they have the same characteristics on average, because there's no decision point as to which group they go into, other than, say, flipping a coin or rolling a dice. And this means that causal inference is usually valid. And this is why, in general, we like randomized control trials, where we enroll patients, randomize them to a treatment or control group, and ultimately compare their outcomes at the end. So one way to deal with some of those systematic errors I was talking about would be to run well-controlled randomized control trial. This doesn't necessarily save you from measurement error. You still have to measure things in a randomized control trial. It doesn't necessarily save you from selection if certain patients choose to not participate in the trial for whatever reason. You can still end up with a selected sample. But it does ensure that you don't have to worry about confounding, and it does ensure that you at least have similar groups for comparing whatever it is you want. So one way to sort of minimize some of those issues I just talked about is through randomized designs. Obviously, that's not always possible. For logistical or ethical reasons, sometimes we can't randomize. So a logistical reason would be that randomized trials are very expensive, or maybe the patient population is quite limited, so it would take too long to recruit enough patients. Ethical reasons would be, in some cases, certain exposures that we're interested in, it's not ethical to randomize a patient to receive them. So for example, if we were studying a harmful exposure like smoking, we can't necessarily randomize individuals to smoke versus not smoke. In those situations, we have to use observational data or data that's already been collected. And here, causal inference is only valid under really strong and usually untestable assumptions. And so randomize when you can, but when you can't, you have to rely on other sources of data, and you have to be willing to make strong assumptions about those sources of error I mentioned. So you have to be willing to say, I've minimized selection bias, confounding bias, and measurement bias in an observational data set in order to make causal claims. It doesn't mean these data aren't valuable. It just means we should be cautious when we interpret weaker study designs than a randomized experiment. And so you can see this little evidence pyramid on the right shows you that at the bottom, these are correlation type studies. These would be more the descriptive questions I mentioned earlier. And then as we move up the pyramid, we have increasingly rigorous study designs. So observational causal questions, and then experiments where we actually randomize participants. Generally speaking, the studies at the bottom are cheaper, and that's why you see many more descriptive studies in the literature than you see explicitly causal studies, and even less randomized control trials. That's not necessarily a bad thing. It's just you have to interpret each sort of accordingly. Related to designing those studies is something I get asked about a lot, and this is power and sample size calculations. So almost always, whenever we're starting a study, whether it's a randomized trial, an observational study, a chart review, whatever it may be, often it's encouraged or asked to do some sort of power or sample size calculation. And this is to say, basically, how many patients should we collect into this data set in order to make our results meaningful? And this can be valuable. Certainly, if we're designing a study like a randomized trial, it's important to know how many patients we're going to need to answer the question, because that directly informs the timeline, the budget, the feasibility. Often, however, we have actually pretty finite available sample sizes, and this would especially be true in pediatrics. And I would also say there's often value in doing a study regardless of the statistical power, especially for more descriptive studies. And what this sort of leads to in some cases is that we have some fixed sample size. In this figure, say it's around 47 patients. We work backwards from that sample size to come up with some effect size that we can power the study for. And then we say, okay, well, we have enough power to do this study. This is sort of a dance that can be performed between, statisticians and investigators to justify a study that's going to be done no matter what. I would argue in many cases, this is sort of a waste of everyone's time, and that we should just go ahead, even in a low power descriptive study, because that information might still be the best available. So an example would be, let's say we were studying a rare cancer at BC Children's, where only 10 kids a year on average are having this disease. It's very unlikely we're going to have enough data to make any really high precision claims about that particular cohort. And that's because there's just not that many people who have that disease. That being said, the information on the people who do have it is still useful for planning in the future, or it could be combined with information from other centers, other small publications from other hospitals, in order to build up a bit of an evidence base. In this sort of example, a power calculation will tell us the study's not worth doing because we can't detect anything. But actually, there are sort of other motivations maybe for carrying the study forward. So here I would say there is a time and a place for these, but many studies I see probably don't require power or sample size calculations. So just to summarize that, these are useful when we have a true sense of the minimal clinically important effect. We're enrolling patients prospectively, so it's going to cost time, resources, money to enroll patients. And when there's a financial or time cost associated with recruitment. A power and sample size calculation is less useful when we plan to do the study regardless of the power or sample size. If the data is retrospective and low cost, if it's just going to a database or going back to charts, we're probably able to do that regardless. Or when there's no established clinically important difference that we're looking to detect, perhaps we're doing some hypothesis testing. In most cases, it's usually better to frame these calculations around precision anyway, and not a single hypothesis test. All that being said, I have found in the studies I'm involved in, often granting agencies or ethics boards want to see power calculations no matter what. So we end up sort of doing this dance that I described on the last slide. But broadly speaking, I think in many cases they're not necessary. And sort of, don't actually change the outcome of the study. So the last sort of misconception or pet peeve I'll talk about is actually around data analysis. And this one is something you see quite often, and it's categorizing continuous data. So often in our data sets, we have continuous variables, things like age, body mass index, blood pressure, and often these are put into categories. So we might say we're going to take BMI and we're going to break it into normal, overweight, and obese. Or we're going to take blood pressure and break it into hypertensive versus non-hypertensive. Or age, we might split at, say, the median value of the age in the data set. And this is done often because people think these are more clinically interpretable categories, and that may be true. But it comes at a fairly large statistical price. So whenever we categorize continuous data like this, we, number one, reduce statistical power for the same data set. It assumes that risk is flat within the categories, and it treats patients just below and above a threshold as completely different. And so you can sort of see that on this graph on the right, where let's say we categorize patients based on being above or below 50 years old. So the x-axis shows age. You can see this dotted line is the 50 years. And on the y-axis is the risk of some outcome that we're interested in studying. If we categorize age above and below 50, we assume that the risk is exactly the same between 0 and 50. And then it's exactly the same between 50 and whatever the oldest age, say 100 is in this data set. And that there's a big jump. The minute you turn 50, you jump from low risk to high risk. This is obviously a little bit silly. In principle, there shouldn't be a huge difference between someone who's 49 years old and 11 months and someone who's 50 and 1 month. But the way it's modeled by categorizing the continuous variable treats those two as very different cases. What you can see in green behind this is what's called a spline. This is a flexible way of modeling continuous data. And here, rather, it shows sort of a gradual increase in risk as you get older, which is likely more true to the biological relationship. So whenever we sort of categorize data like this, we're making some pretty strong assumptions, pretty strong modeling assumptions. It doesn't mean that it can't be useful to report results by clinically meaningful strata, but that can be done after the modeling stage. So after we fit a model that doesn't categorize the data, we can use the results to say, show the risk for a 20, 30, 40, 50, and 60-year-old. So when modeling, it's always better to use the continuous data. This is something that you see in lots of papers and generally is again not recommended. So the final point briefly before I wrap up and take any questions is that number 10, a plug for myself and other biostatisticians, is that we can help at all parts of study design. So there's a famous quote that says to consult the statistician after an experiment is finished is often to ask them to conduct a post-mortem exam. So we can help at the early stages to help design a study to ask the right question. So this descriptive versus predictive versus causal, and think about the types of data you'd need. Do some mitigation for those sources of bias we discussed, so selection bias, confounding, measurement. Inform the study design. So this could be, in some cases, a power sample size calculation. It could be the type of study we might want to run or the type of data source we might want to use. And we can help plan how to collect the data. For example, I would encourage people to collect age continuously instead of asking people, are you above or below, 50 years old? So generally, these are some of the most consequential decisions, and the data analysis can help with some of these things, but really a lot of the key methodological choices happen at the design stage. So I would encourage anyone who's designing a study to feel free to reach out to me or my team to discuss some of these points. And so with that, I want to thank everyone for your attention and listening to me meander across a few different topics in biostatistics. I hope at least some of those were relevant to your work, and happy to take any questions. Is my face back now, Emily?
I can see you. Yeah.
Okay.
You're good.
Right on. Good.
I don't see any questions in the chat yet. Does anyone want to unmute and ask Steph any questions?
Yeah, thanks, Shanlia. I have a question. This is Nadia. Can you hear me?
Yeah. Hi.
Perfect. Thanks a lot, Jeff. That was super helpful. I had more of a question around interpretation of non-significant results, and I know that you touched upon this a little bit, but I'm finding I have statistical power. I'm even getting, sort of a larger effect size, but not statistical significance. And I don't want to, like you said, put so much emphasis on that, but how would you kind of recommend interpreting that?
I mean, my biggest comment to people who have studies that are not statistically significant is to look at the confidence interval for whatever it is you're estimating. If that confidence interval includes values that are important, clinically important in one direction or the other, the conclusion of the study is that you don't have enough precision to rule out an important effect. And that's a modest conclusion. Like that's more modest than saying there's nothing here, but it actually reflects the data that you have. On the other hand, if you had a confidence interval that was very small and centered closely around no effect and sort of ruled out most of the important effects, you could say, hey, there's no difference here. And our data is sort of like the precision of our data is compatible with nothing important. Therefore, we think this exposure, this treatment is not useful. We're not interested in it going forward. But as soon as you have a wide confidence interval, which is typical for a lot of studies, that includes important effects, you don't have a definitive conclusion with your data. And like, unfortunately, that's a less sexy conclusion for a paper, but it's actually a more accurate one. And so I often have this comment on like papers I'm on as a collaborator is encouraging people to change the language around we saw no difference here. It's actually we saw an uncertain difference here and we're not actually sure. We can hypothesize, but that's sort of it. So
okay.
Yeah. I don't know if does that answer your question?
Yeah, that's helpful. I think I was leaning towards saying no difference, but you're right. It's a wide confidence interval in either direction. So
yeah, so then it's the data is compatible with a big difference or a big difference in the positive or negative direction, and all that says is the data is quite uncertain, and like that's okay. It's better than closing off avenues and saying there's nothing here, no one else should look at this, because people only read the abstract or the final conclusion of a paper. So I think
thank you so much.
Yeah, thanks for the question.